Hello, everyone, and welcome to our live session, our rescheduled live session. So I'm glad to see everyone here got the message. Thank you for your understanding. We are here with you on Monday, June 17th. My name is Matthew. I'm one of the course staff for our online classes. I also help run things behind the scenes here at Teach Astronomy, and I will let Professor Impey, go ahead, Chris, introduce yourself, say hello, welcome everyone, then we'll get started with questions from the chat.
Okay, it's good to be back with you. This is the live session for anyone who's on one of our MOOCs or anyone who just encountered us through some other means, and I will be able to take any question on astronomy and hope that I can answer it.
Excellent. So for those of you who are with us for the first time, the way it works is we ask that you type your question into the chat. I will grab those from there and I curate them. We try generally to go in the order that they are asked, but we jump around to give more people a chance to get questions answered and to cover a variety of topics. We're going to keep these at an introductory level, and please ask your question only once in the chat. We see all the questions that come by. And if we don't ask it immediately, either it was too high level or we're trying to give other people a chance to get a question. We appreciate you being here. For those of you who are just joining us on the channel, make sure you like and subscribe, click that bell icon, then you'll hear about new upcoming live sessions. Our next one will be in 2 weeks. For our first question today, we have a question from Adrian Murray, who asks, is spaghettification a large process when actually just how can you talk about the process of spaghettification for a black hole? So this is when somebody falls into a black hole. Is this a long process? Is it something that would happen instantaneously? How would that work in, quote, real life?
Right, so it's obviously a colloquial term that relates to what happens if a human or object or living object or organic matter falls into a black hole. And as spaghettification implies, there's an extreme stretching. So what's going on is the tidal force, which is the gravity as you approach the event horizon of a black hole is very strong, but the difference in the gravity over a short distance is strong too, and that's the stretching force. So it's not the total gravity that matters, it's the differential gravity. And that difference in gravity is what causes the stretching and spaghettification. Now, because it's a stretching of space-time, tidal force on space-time, the stretching happens at all scales simultaneously. So it's not as if someone in a child's game, someone was pulling on your feet and someone else was pulling on your hands and just stretching you that way. This is stretching your body, but also stretching your muscles, your fibers, your bones, down to the level of individual nerves and molecules. So nobody knows really what that would be like to a person, and it's of course unlikely you could survive it. The process is not super fast, it's not super slow. It occurs on the same time scale as falling into the intense gravity of a black hole. And the free fall time into a solar mass black hole from 10 to 100 Schwarzschild radii is probably a few hours. So that's roughly the time scale over which this happens.
Excellent, thank you very much. The next question that we have is from Dr. TK Subramaniam, who asks, what is going to happen to the present space shuttle, let's see, from the Boeing company? Well, so it sounds like they're asking kind of two different questions, but I think they're asking not about the space shuttle, but about the new Boeing space capsule. So
Right.
Have you heard about what's happening to the present space capsule from Boeing, which has developed some kind of technical problem? Are you familiar with that? Can you talk a little bit about anything you know going on with that capsule?
Right, so this is called the Starliner. This is Boeing's a version of a replacement for the space shuttle, which was retired over a decade ago. The alternative, of course, is SpaceX, who already have launched astronauts to near Earth orbit. And in fact, since they've done it successfully and have a much cheaper financial model, many people wonder why NASA is working with Boeing, who have a history of big cost overruns, and the Starliner has had enormous number of delays and technical problems even up until its successful launch to the space station just recently. And the answer is NASA craves redundancy. Having been stuck with a situation where the shuttle had to be grounded after 2 fatal disasters, America was left with no way of getting astronauts into space for a decade, and NASA never wants to be in that position again. So that has led NASA to put its faith and investment into Boeing as well as SpaceX. But many people see the Boeing Starliner as an extremely expensive and trouble-plagued project. It is part of the Artemis mission, a series of missions which will take astronauts back to the moon late next year or early the year after. It seems like Boeing will work the bugs out of this system. You know, they put enough money into it, and that's why it's very expensive. So it looks like the Starliner is not going to go away, and it will continue to be a part of the landscape of how NASA gets astronauts into orbit. But the betting is that SpaceX will continue to do it quicker, more frequently, and more efficiently.
Excellent. Thank you very much. The next question is from Hernan Reyes, who sent an email about the project from NASA's and ESA's X-ray observatories to determine the habitability of exoplanets not too far from Earth. Can you please explain a bit about how Chandra and these X-ray telescopes could find exoplanets around, let's see, what levels and kinds of radiation from their stars could jeopardize habitability of exoplanets circulating around them, and does this change or update the concept of a Goldilocks zone?
So X-ray astronomy plays into astrobiology in terms of understanding the nature of the host star. Exoplanets, of course, are not observed in X-rays. They don't emit X-rays. So X-ray astronomy can only be used to talk about the parent star of the exoplanet. And in this case, X-ray telescopes, including the venerable Chandra Observatory, which has been going for several decades and is in danger of being decommissioned and ended as a mission, is able to weigh in on this subject. The issue is that stars like the Sun are fairly quiet in X-rays, but occasionally have activity and flares. But there's many stars that are much more active in X-rays. For instance, dwarf stars have a lot of X-ray flares. They're more X-ray active, even though they're less luminous stars visibly. And so by looking at the X-ray properties of the stars where we know they're the nearest exoplanets, those within 10 or 20 light years, we'll get an idea of how potentially hospitable to biology those environments are. Having an X-ray active star doesn't say that there couldn't be life on a planet. It may increase the requirement that the planet have a thick, almost smotheringly thick atmosphere to protect against that high energy radiation not being able to penetrate it, or a strong magnetic field and therefore deflect the high energy radiation that way. So X-ray, highly active X-ray stars, in this particular X-ray flare stars, are considered not good habitability candidates for exoplanets, and astronomers might sort of end up ruling them out of their list of objects to follow up. So this is the vital piece of the landscape. It's not simple enough, though, to determine habitability, because habitability has so many variables, and in the end you need to know much more details about the geology and atmospheric content of the planet before you can say that the star's activity renders it uninhabitable.
Thank you. The next question is from the Psycho Messiah, who asks, there is news that NASA has predicted a nova explosion sometime this summer. How accurate can such a prediction be? And if true, what will be visible to the naked eye?
So nova are a recurrent solar atmospheric phenomena where the atmosphere flares up and then the emission rate goes up, so the brightness of the star goes up. More nuclear fusion, and then it recedes. The lower density quenches the reactions, and then the atmosphere settles in again. And some of these novae are recurrent novae. They're not truly cyclic in a sense of being strictly periodic, like some orbiting star phenomenon. They are predictable at some level, but not with high accuracy. Usually as the nova starts to become active, it shows telltale signs of incipient activity, and that's what NASA's seen. So the prediction for activity in this summer is a little generic, and it's not super precise. And it's also very imprecise in terms of what the peak brightness of the nova will be. So basically, astronomers can't really tell. But it's potentially at the level where it could rival some of the bright stars in the night sky at the peak of the nova.
Jerry Greer has a question. Can you talk about the effects on Earth if a star went nova or supernova? How far would it have to be? I mean, he poses a 30 light year distance, but can you talk about what would happen at various distances or when it might affect Earth?
Yeah, for supernova, nova activity is a lot less luminous than supernova, which can be thousands of times more luminous. So supernovae have the largest reach in terms of their high energy radiation, gamma rays, cosmic rays, and so on, and impulsive neutrinos as well. The 30 light years is the sort of round number for where proximity to a supernova will have global effects on the Earth, affecting the atmosphere, eroding the ozone layer, the protective ozone layer. That's one of the first effects. But at 30 light years, a standard type 1 supernova will not be catastrophic to the Earth. But there will be significant effects, and those the ozone layer depletion would lead to high mutation rates and a lot of damaging radiation coming to the surface. Once you get closer than 10 light years, then the effects can become truly damaging in the sense that the radiation from the supernova may actually destroy organisms on the Earth's surface and in the top layers of the oceans. The odds of a supernova within 10 light years are extremely low because we know all the stars within 10 light years, and the number that are massive enough to die as a supernova is a very small number, and none of them seem to be on the edge of dying.
The next question is from Wisdom and Joy, who's on with us live. I have a question about black holes. Is it true that they also eject matter? Can you explain how that phenomenon works, if true?
Black holes eject matter from their environments. So the black hole, of course, is black. Nothing can escape, and matter falls in. But the immediate environment of a black hole is an intense gravitation and radiation environment. And so the material that swirls into a black hole typically swirls in on the equatorial disk, because the black hole is spinning, and so it's surrounded by an accretion disk. And it's this disk of material which is sort of the reservoir that will eventually fuel and grow the black hole. That material is very hot. In the disk, it could have temperatures of hundreds of thousands or a few million Kelvin, and so be shining brightly in X-rays. And then the nozzles, the polar jets around the black hole, are also acceleration zones for high energy radiation. So while the black hole remains black and nothing can escape, the environment of a black hole is a gravitational engine which creates intense radiation.
The next question is from an email from Terrace, who asks, some of the stars in the night sky look red, orange, or bluish according to their surface temperatures and their classification in the HR diagram. Our sun looks white in space, though it's classified as a yellow star. When the sun becomes a red giant, will it look red in space? Do these other aliens around these other stars that are blue or red see their stars in the sky as red or blue, or would they see them as white also?
So colors of stars are interesting because the best way to measure the true color of a star is, of course, with an electronic detector, which measures the amount of radiation at all the wavelengths of the visible spectrum. And that's our best sense of the color of a star. The eye has its own sensitivity curve, so the way something looks to the eye depends on the functioning of the eye and where the peak sensitivity is. And then the second thing that's going on is the atmosphere changes the color of a star. So part of the reason why the sun appears white from outside the Earth's atmosphere but yellow inside is because of the reddening effect of the Earth's atmosphere. So that's a real effect of the atmosphere. So true colors of stars, of course, should be observed outside the atmosphere from like a Hubble Space Telescope or something like that. And the colors are quite subtle because the broad spectrum response of the eye means that it's not really sensitive to large color ranges. There are very few stars that are so cool that they actually look even slightly pink, and there are very few stars hot enough that they look slightly blue. Most of the colors you see by eye are very subtle. Would aliens see the same thing? Well, if they had eyes, they would. So it's always a question what the sensory apparatus of an alien life form would be. And there's no sense or requirement or necessity that they would have vision the way we do. So I think the odds of aliens seeing stars the way we do are actually very low.
The next question is from Nicole, who's on with us live. Can you talk about some careers related to astronomy?
Well, related to astronomy, because astronomy uses computers and computation so much, are a lot of fields in computational science and programming. I mean, these are very good jobs, of course, and good careers, and there are a number of astronomers who've moved from pure astronomy research into a sort of work with supercomputers and work on computation and algorithms and programming, because astronomers in that work tend to push the envelope of computation. So that's a very big set of jobs that are available to astronomers who are technically trained and know how to do computer simulations. Another set of jobs that's far from the field of astronomy and academic astronomy is people who work on detectors and work on the instrumentation of astronomy. They tend to have a wide range of skills, in possibly dealing with thermal physics or electrical engineering or the way solid-state detectors work. So people who work on instruments for astronomy research have very marketable skills and can move into other jobs. And then the third area, perhaps, of jobs that aren't directly from astronomy are people who are good at communicating astronomy and science in general, or writing about it, and they can move into the sort of science communication regime. Doesn't have to be strict journalism. You can write articles, popular articles, blogs, websites. There are various periodicals that take astronomy articles, so science communication is another career path.
Thank you very much. The next question is from Victor Rosa, who asks, how has the development of new space telescopes shaped our understanding of distant cosmic anomalies and the age of our universe?
The space telescopes have been crucial in understanding cosmology and the age of the universe. Remember that there's always been bigger telescopes on the ground than there are in orbit. Hubble Space Telescope's mirror is 2.8 meters, and that's a small mirror compared to large optical telescopes on the ground. It's not even in the top 60 or 70 largest mirrors for telescopes. But by being above the Earth's atmosphere, the sensitivity is extremely high. And so the Hubble Space Telescope obviously had a large role in measuring the expansion rate of the universe. That was one of its early key projects, and in finding the acceleration of the universe in the 1990s, and in mapping out the early expansion of the universe through distant objects. And that mantle's been continued by the James Webb Space Telescope in the last 2 years. So space telescopes are very useful in exploring the cutting edge of cosmology, but they never really answer these foundational questions alone. There's a large number of ground-based observatories working on the same problems, and they are extremely important too.
The next question is from Ashley Kraft, who asks, how is the University of Arizona astronomy program?
Our astronomy program is well reputed and in very good condition. Our university has had its own problems lately. We've been in the news for not good reasons with budget problems. But astronomy is healthy. Astronomy brings in a lot of money. It's one of the rainmakers of the university. So we have grants and contracts worth over $100 million a year. So there's a lot of people in the astronomy program because of all the telescopes and observatories we run and the instruments we build. Steward Observatory overall has about 500 staff. Within that and associated with that is the astronomy department with about 40 faculty, about 60 graduate students, and 300 astronomy majors. So these are all of those numbers put us among the biggest programs in the country.
The next question from one of our live participants, Art Child, asks, can gamma rays be seen by the human eye?
No, gamma rays are invisible radiation, extremely high energy, extremely short wavelength, and extremely high frequency. And so the eye is unable to detect gamma rays. In fact, if gamma rays hit the eye or a person, they essentially cause damage to the cells because they carry such high energy. So far from being able to be detected by humans, they're actually hazardous to humans.
Jerry Greer, who's on with us live, would like to know, are there any worlds in which it rains natural gas?
There could well be. The range of exoplanets is extraordinary, and there are exoplanets that rain down molten lava. There are exoplanets that rain down essentially crystalline diamond-like material that condenses in the atmosphere. So it's quite conceivable, although I don't know of a specific example where you could have an exoplanet where there are hydrocarbons, and those hydrocarbons precipitate out of the atmosphere. And that's what natural gas is. It's a sort of hydrogen-carbon molecule. And certainly those hydrocarbons are going to exist on exoplanets. That's not going to be an unusual thing.
Priyanjali asks, is life possible on a hot Jupiter?
Astronomers are doubtful that life could exist on a hot Jupiter, and the reason is just the conditions are so extreme. Even on normal Jupiter, our Jupiter in the solar system, it's not clear that there's a habitable area anywhere down in the planet, even though there is a zone. There must be a zone going down through the atmosphere where the temperature is temperate, but there's no solid surface. With hot Jupiter, you're not even in that situation, so the whole planet is kept at a temperature of 1,000, 1,200, 1,400 degrees Celsius by the intense star that's very nearby. And so this is way beyond the habitable zone. There's no way it could be liquid water. You couldn't retain structure with molecules. And so hot Jupiter seemed the least likely exoplanets to have life.
John Kingicher sent an email asking, what are some of the new telescopes and observatories that will become operational in the next, say, 20 years?
Well, on the ground, we are seeing the completion of, or the progress on 3 huge new telescopes. The first to get light would probably, before the end of the decade, will be the extremely large telescope of the Europeans, located in Chile, and about quite effectively a 39-meter telescope. Coming next, likely, will be the Giant Magellan Telescope. That's our project out of the University of Arizona, where we make the mirrors. All 7 mirrors have been made. The project does need extra funding, hopefully some from the federal government. And first light for the GMT is probably 2031 or 2032. The third is the Caltech Large Telescope, or sort of the 30-meter telescope. TMT is the acronym, out of the University of California and Caltech. The problem there, apart from funding in general, these are $2 billion facilities basically, is that their site in Hawaii on Mauna Kea is controversial because Native Hawaiians don't really want another large telescope up there. So that construction is stalled. So that telescope also, at the very earliest, will not be online until 2032 or 33, and it may have to relocate to the Canary Islands. Those are the 3 huge new optical telescopes under construction, and there are designs or plans for what it might take to build a 100-meter telescope, but that's on a time frame that's many decades away.
Nicole Escalante is on with us live and asks, how did we discover the idea of dark matter?
The first inkling of dark matter came actually in the 1930s and 40s, when the Milky Way seemed to have a gravitational force and movements of stars that indicated matter that couldn't be seen in the accounting of the disk of the Milky Way. That was a hint of dark matter. It wasn't really very strong evidence at that point. The best evidence started to emerge in the 1970s when people measured what are called the rotation curves of spiral galaxies, which is looking at nearby spiral galaxies and their velocity of their stars moving out from the center of the galaxy, where they're not moving at all, in the disk. How does the rotation speed vary with distance from the center? And according to Kepler's laws, once you're beyond the bulk of the mass of the galaxy, the rotation speed should decline with the inverse square root of the velocity with the distance. And that was not seen. Spiral galaxies maintain constant rotation out to the visible edge of the galaxy, which indicated there was unseen or dark matter causing those high rotation speeds. That was controversial evidence in the 1970s, but it got stronger through the 1980s. Then elliptical galaxies were found to have the same phenomena, very high stellar velocities indicating dark matter. And then a whole series of other pieces of evidence came in the 1980s and 90s, like gravitational lensing, also strongly indicating dark matter. So it emerged gradually, I would say, the evidence for dark matter over a period of 20 years.
The next question is from Jerry, who asks, can a star transform into a planet if it loses mass?
No, a star is essentially a fusion reactor. It's a spherically contained ball of plasma where fusion reactions are occurring at the core, and there is nothing solid in there because the temperature is so high in the interior, where fusion is occurring millions of degrees, that no matter can be solid. So there's no solid anywhere inside a star. The entire star is a plasma, so it's just very far from being a planet. So you couldn't really change the star's properties and somehow turn it into a planet or a solid.
Ashley Kraft would like to know, are there any updates on the Mars exploration projects or developments at the University of Arizona?
Well, so the Mars the Mars rovers, had a very long life. And now, of course, we have two Mars rovers, the second generation of Mars rovers, Curiosity and Perseverance, and they're both still active. And they're both doing really good work. University of Arizona has been associated with all the rovers, if not building them, then certainly designing cameras for them. So rovers are very sophisticated technologies that we know how to work on Mars, and we've really had most of our information from a series of rovers that started with the Pathfinder, which was a tiny little rover in the 1990s.
Randy Cockrell, who's on with us live, asks, what are your thoughts on the idea I have heard that life is most probable in spiral galaxies?
That comes from the fact that spiral galaxies have a lot of young stars and they have a lot of heavy element production. And so you can measure what the abundance of heavy life important elements like carbon, nitrogen, and oxygen is. And the abundance of those elements is much higher in spiral galaxies than elliptical galaxies. Because elliptical galaxies have formed most of their stars very early on in the universe when the universe didn't have a lot of heavy elements. And then they've not been forming new stars since. So there's been little recycling of gas. And that is a big difference. And so that's the basis of saying that biology is much more likely in a spiral galaxy than elliptical. But it can't be a blanket statement because stars in elliptical galaxies do have some heavy elements, and it's not clear, of course, how much abundance of carbon, nitrogen, and oxygen is required to have biology.
The next question is kind of an incredulous statement, but they would like your reaction to it. How can anyone say that the Earth is flat when the ancient Greeks discovered that the Earth is round?
The persistence of the flat Earth myth is intriguing to social scientists and frustrating to physical scientists who just think it's a willful denial of all the evidence of science for 2,000 years. As you say, ancient Greeks knew very well by logic, geometry, and some observation that the Earth was round, and more or less what its size was. Flat Earth emerged in medieval times and the Dark Ages when a lot of the Greek knowledge was lost. But the fact that it persists in the modern age is kind of puzzling. But people believe a lot of strange things. It's an intuitive that you don't see the curvature of the Earth, and so if you're just believing the evidence of your eyes, maybe you could be doubtful, but you would have to willfully ignore a lot of other evidence. You can see from the history of Google search, you can track flat Earth, in other words, how often people search on the term flat Earth, and it's fluctuated, and it had a surge in the last decade. So flat Earth belief, or at least in terms of search, seems higher than it was 10 or 15 years ago, which is a little discouraging for science educators.
Well, the next question is from Terrace, who asks, how does the sun's activity influence human health?
Well, the solar cycle has an effect on the Earth. It has an effect on the Earth's climate. It has an effect on the radiation environment of the Earth. And in particular, when there are strong solar flares, more than just the standard sunspot cycle, then the radiation environment of the Earth can get quite intense. There can be a lot more UV radiation and cosmic rays. I would say these are minor impacts on human health because our atmosphere is thick and protective, and the solar wind and the magnetic field of the Earth deflect a lot of high energy particles. So this is probably one of the least impacts on human health compared to other things.
The next question is from Victor, who asks, how does debris left in space affect astronomy and data collection from the ground?
Debris in space is becoming more of a problem for astronomy, in particular the constellation of satellites launched by SpaceX and other companies. These are tens of thousands now of low Earth orbit satellites that reflect the sun's radiation. So when they're on the horizon near sunrise or sunset, they reflect the sun's radiation off their metal surfaces down towards telescopes, which see them in their images, their deep images. That's really how astronomy's mostly been affected by space debris. It's not debris in a sense, it's actually satellites that people are deliberately launching. They're small, they're like nanosatellites or microsatellites, but there's enormous numbers of them.
The next question is from Eliezer, who asks, recent research indicates the possible presence of a large object on the outskirts of the solar system, causing orbital anomalies in other objects. Could this be some kind of large planet?
There are orbital anomalies in the outer solar system, and this is a subject that's been pursued for a couple of decades. And there have been claims and then false alarms for that same length of time over a big planet, Planet 9 or Planet X or whatever you want to call it, a Pluto or a much larger planet quite far out. But none of these things have stood the test of time. And the reason is these are very far away. We're talking about distances of 40, 50, 60 astronomical units, where the Earth-Sun distance, 150 million kilometers, is 1 AU. So it's very hard to measure these motions and be sure of the influence of a more distant object. So this is difficult work. It needs a lot of data. It needs monitoring over a long period of time to track motions of objects that are moving quite slowly and are very far away. But at the moment, there's no strong evidence for anything other than a handful of Pluto-like objects in the Kuiper belt or beyond the edge of the solar system. Certainly nothing substantially larger.
The next question is from Elaine and Eliza, who ask, what is the status of the current experiments looking for dark matter?
There are many dark matter experiments, a dozen, perhaps 15, that are competitive. Most of them are physics-type experiments because the perception is that the dark matter particle is a subatomic fundamental particle. And these experiments, many of which are in deep mines to protect from cosmic rays and extra radiation, have to take a lot of data to get somewhere. Because dark matter interacts so feebly with normal matter, basically just by collisions, and it has no interactions with light, that you need an enormous solid state or liquid detector to look for the rare collisions of a dark matter particle with normal matter and then detect that. And these experiments have been underway for a while, some more recently than others, and many of them will get a significant result, but not for a few more years. So within a few more years, if all these experiments with different designs fail, then there will actually be a crisis in astrophysics, because we'll start to be ruling out the most plausible dark matter candidate and not really be left with any other good physical candidates for dark matter.
The next question is also related. Lawrence K. asks, where did all the antimatter from the Big Bang go? If the Big Bang was a quantum event, could there be another universe where antimatter dominates? And then there's a little bit more we'll ask after that.
There's two questions there, so I'll answer them both. I'll treat them as separate questions, actually. Where did the antimatter of the universe go? A good question, because in the Big Bang, radiation, the intense radiation of the Big Bang, was able to form particles and antiparticles in equal numbers, because this is a physics phenomenon that we're familiar with. In the lab, you can have radiant energy create particle-antiparticle pairs. So that happened on a huge scale in the early universe, and they were roughly equal numbers, but not exactly equal numbers. The bet is that in the fundamental physics of how the forces of nature unified, there was a very slight residual asymmetry in those forces as the universe cooled. And that led to a very slight excess of what we would call matter over antimatter. So when the annihilation of the matter and the antimatter happened, there was a tiny little extra bit of matter left, and then a lot of radiation. And so that's how you explain a universe that we see, which has 1 billion photons for every particle and essentially no antiparticles. The second question, I separated them. What was the second part of the question?
The second part of the question was, if the Big Bang was a quantum event, could there be another universe where antimatter dominates?
Yeah, so in the Big Bang scenario where it is a quantum event, and that makes sense because the universe was once, by projection back in time, the size of an atom or smaller, so the universe's origin, if we're understanding it at all, is a quantum event. And yes, it is plausible that the quantum event that led to our universe was not the only one, and you could have other quantum events and they might have different physical properties or different laws of physics. And certainly that could include a universe where the asymmetry went in the other way and you ended up with antimatter dominated universe, or for whatever reason only antimatter was created. So it is entirely plausible, though highly speculative, that you could have an antimatter universe.
And then the final piece of this is, and you mentioned it a little bit, but can antimatter be produced in a lab, and how is that done?
Yes, antimatter can be produced in a lab, but in very small quantities and at great expense. The biggest laboratory for antimatter is at the Large Hadron Collider in CERN, the particle accelerator, because that facility can make quite large volumes of antiprotons. And then you can make anti-electrons with a separate process, and if you can somehow cool the containment region sufficiently, the electron could attach to the proton, or the anti-electron, the positron to the anti-proton, and you get an anti-hydrogen atom. So antiprotons have been made in large numbers in standard particle accelerators. Combining them with positrons to make anti-hydrogen, and actually an actual antimatter atom, is much harder, but it has been done too. These don't survive for very long because they're going to eventually annihilate with the container or its surrounding region, so really they hardly ever last any length of time. I think the record in the last few years for doing this is to contain a very small number of anti-hydrogen atoms for something like 10 or 15 minutes before they disappear.
The next question is from Wendy Traver, who asks, how relevant is a magnetic field to the habitability of planets and moons?
A magnetic field is quite important, astronomers and astrobiologists think. It's also hard to measure. So they're sort of indirect methods for inferring the magnetic field of an exoplanet, but they're not reliable. There's no direct measurement. So what does it mean? Well, magnetic field for the Earth is clearly important for the habitability of the Earth because it's a shield. It acts as a shield against intense radiation from our sun. Mars, it's a much smaller planet, which does not have a liquid metal core. It's lost its magnetic field, even if it had one originally. And Mars is irradiated and essentially sterilized. It has a thin atmosphere as well, but it's also sterilized by radiation. So the magnetic field as a protective agent for potential biology seems very important. But as a natural part of planet formation, planets will form with magnetic fields because the solar nebula they form from was threaded with seed magnetic fields. So it's not implausible that exoplanets in general will have magnetic fields that help their habitability.
The next question is from Angelo Moro, who asks, I would like to know if we know how the lines on the surface of Jupiter's moon Europa are formed.
It's likely that these are just fracture seams and fractures in the ice pack. So we know that the Europa's surface is ice, and it's quite thick. It's anything from 1 kilometer to 10 or 20 kilometers thick. We also know that there are seismic forces, there are geological seismic forces, and then there are stresses caused by the fact that there's a liquid ocean under the ice cap. And so these stresses and stretching forces are likely to crack the ice pack and lead to this kind of seams and lines that we see.
The next question is from Mahi, who's on with us live. How does the image of the cosmic microwave background come to us intact from billions of years ago when we've all been there at that point and been in those, at one point we were all sort of in the same muck, these quantum vibrations. So how is it that we see it from that long ago?
So when we look into the microwave sky and see the microwave background radiation with a temperature of 3 Kelvin, so just very close to absolute zero, these are photons that have been traveling for 13.5 billion years through the universe as space has expanded, the universe has cooled, and those wavelengths of radiation that was originally very hot have been stretched to very low energy microwaves. So we're embedded in this radiation. It doesn't have a directional sense. It's a sort of bath of radiation, which as it travels through space is being degraded and stretched in energy. And that's just been happening continuously since the radiation was released as atoms became stable as electrons attached to protons in the early universe.
Excellent, thank you. The next question is from one of our live participants. Jerry Greer asks, can you talk a little bit about metallic hydrogen, describe it, and is there any way it could ever be used by humans?
So metallic hydrogen, hydrogen in the normal world at normal temperatures and atmospheric pressures is of course a very light gas. However, if you have a situation where extremely high pressures exist, you can force hydrogen into such a high density state that the electrons are shared and can travel through the material in a sort of quasi-liquid situation. And that's the definition of a metal. So under extremely high pressures, hydrogen can become metallic. And that's what we think happens at the base of the atmospheres of Jupiter and Saturn, although we can't prove it. Now, in the lab, I think metallic hydrogen has also been created because of the enormous pressures it's possible to create in a lab. So we started to learn about metallic hydrogen properties from lab experiments too.
The next question is from Eugene, who asks, have scientists recently observed stars being surrounded by Dyson spheres? Do you believe that these exist or could be alien built?
There's no good evidence for Dyson spheres. Dyson spheres is a construct, it's a hypothetical technology of an advanced civilization where rather than accepting the small amount of radiation that their planet intercepts, as we do from the sun, 1/1000th of its radiation, to gather more than that tiny fraction, you build an energy trapping sphere around the star, close to the star, and then in principle you can capture not all but most of its radiation, a huge amount more than you get just by being far from it. It's not a solid sphere because that would not be rotationally stable or a structurally sound object, so it's a skeletal type structure. It would affect the way a star appears because that trapping of that radiation would re-radiate waste energy in the infrared. So the signature of a Dyson sphere, should they exist, is a star where there's an anomalous amount of excess infrared radiation, sort of waste energy from the Dyson sphere after it traps the high energy radiation. So there's been no convincing detection of a Dyson sphere. It's a very hard observation to be sure of because they're dust particles that can re-radiate solar energy when they're close to the star. So there are normal astrophysical mechanisms that can mimic this simple signature of a Dyson sphere. The odds of actually seeing a Dyson sphere by imaging a star and seeing a structure around it are very small because stars are simply too far away.
The next question is from a user called Obama. Why do quasars shoot out? So I assume they mean like what are the jets of
Yeah,
quasars? Like why
right.
why is it that we see those jets and how does that occur?
Right. So quasars are quasi-stellar objects or quasi-stellar radio sources sometimes. Um, and they are supermassive black holes at the centers of galaxies with masses ranging from 4 million times the mass of the sun, say in the Milky Way, up to 20 billion times the mass of the sun in some large elliptical galaxies. Many of them, but not all, have jets, bidirectional outflows and acceleration of particles and plasma along the polar axis of the spinning black hole. So the spinning black hole, the center of a galaxy, will essentially create an evacuated zone around its poles, and the accretion that's occurring on the equatorial plane from the accretion disk will funnel up and above in the north and south polar regions, and then be accelerated by the magnetic field of the black hole playing out into space, acting just as a particle accelerator. And that's what causes the jets. So the jets are very high energy plasma, but also very diffuse, very thin plasma at a very high temperature that's emitting electromagnetic radiation across the spectrum, all the way from radio waves to X-rays.
The next question is from one of our live participants. Yashwanth asks, what is the best way to start learning astronomy from basics, and where can I find out about problems related to astronomy that are yet to be solved?
Well, obviously, I'll start here, right here at home. I mean, we have astronomy courses with Coursera, an introductory astronomy course. So if you want to learn on your own time and at no cost, unless you want to pay for a completion certificate, then our MOOC with Coursera, Astronomy Exploring Space and Time, is highly recommended, of course. We put it together. If you want to go beyond that and find out about unsolved problems in astronomy, that's a little harder because now you're at the research level. Where the astronomers go to learn about this stuff, in addition to the academic journals, is the archive, as it's called. Archive is spelt little a, little r, capital X, little I, little v. That's the archive where preprints are. It's a preprint server, and that's where the basic research results of astronomy, and you can filter on keywords, dark matter, dark energy, whatever you want, to kind of figure out what the state of the art of the field is. But this is technical literature, so these are not easy articles to read. I think there are some other magazines like Scientific American and occasionally Astronomy Magazine that also summarize what are big problems in astrophysics that people are working on.
The next question is from Tyler, who asks, if a black hole ever collapsed, do you think that anything that had once been pulled inside would exist again?
No, I think it's a one-way membrane. It's an irreversible process. Whatever structural integrity something that fell into a black hole had, it's lost when it's inside the black hole at these incredibly crushing pressures, and also the differential stretching forces are enough to rip apart any physical object. So even if a black hole evaporated, which they are supposedly doing, according to Stephen Hawking, that evaporation is just turning them into unstructured radiation. So there's essentially no way within black hole theory that you can retain the information, even in the long run, of the objects that fall into a black hole.
The next question is from Tejas Tambek, who asks, the rate at which the universe expands, does it depend on your or a particular frame of reference?
So the local expansion rate of the universe, called the Hubble constant, that's the slope of the diagram of velocity versus distance, it doesn't depend on your frame of reference, because we could measure the expansion rate of the universe from the Earth in our galaxy, the Milky Way. But if you measured the expansion rate from another galaxy, in the sky, within the local universe, you'd measure the same thing, since all galaxies are moving away from every other galaxy. So there's a democracy of perspective here. In other words, no privileged location, which is a statement of the Copernican principle.
The next question is from G, who is on with us live, who asks, realistically speaking, how far are we from mapping out every exoplanet's biosignature in our own galaxy? Are we talking decades, centuries, or even longer?
To map out the biospheres of all exoplanets our galaxy, the answer is never. It's a simply infeasible program. Remember that of the 6,000 exoplanets that are cataloged so far, almost all of them are within a few thousand light years of the Earth. And that's a galaxy, it's 100,000 light years across. So they're all in our backyard. So even if we characterize the biospheres of all 6,000 exoplanets that are cataloged, that's still a very small part of the Milky Way. And even that activity would take an enormous time. So unfortunately, it's very difficult work, much harder than detecting the planet in the first place. And so really, within the next decade, if we're doing well with large facilities, we might characterize the biospheres of a few dozen, maybe 50 exoplanets. That's about as good as we can do in the near term.
The next question is from Ohai, who asks, what are the differences between leptons and quarks? We'll get to the second part after you answer that.
So in the characterization of fundamental particles, leptons are light particles. That's from the Greek for light. And so a lepton, for example, would be an electron or a neutrino. And quarks are heavier particles because quarks are the constituents of protons and neutrons. And so that's a fundamental distinction in nuclear and fundamental particle physics between the light particles and the heavy particles that are in atomic nuclei.
The second part of the question is, why can't quarks travel individually through space like leptons can?
So quarks are subject to confinement because they are retained in an atomic nucleus by a very strong force called the strong nuclear force, and the exchange particle that's characterizing that force is called a gluon. So the word gluon gives you the hint that it's a pretty strong glue. And so gluons are exchanged between quarks in an atomic nucleus, and they act as a very tight binding agent on the quarks, which is to say that the quarks can essentially never escape and become free. If you have a high-energy physics experiment and you bombard atomic nuclei, you can create something called quark jets, where sort of the quarks emerge momentarily and then go back into the nucleus. But free quarks are essentially not seen in nature, and they're not even easy to conjure up, even for a short period of time in a high-energy physics experiment. And it's because of the strong nuclear force.
Elizabeth asks, what happens if Earth's magnetic field reverses polarity, and is there any way to predict this?
Sure. The solar cycle reverses the polarity of the sun, and the Earth's magnetic field has its own magnetic cycle. And so we've seen magnetic reversals of the Earth through history, and you can track this with magnetic minerals over time. So radioactive dating of rocks plus the magnetic minerals shows that the Earth's magnetic field has been reversing with a regular pattern for millions of years.
The next question is from Rajat, who asks, what do gravitational wave data, I was right the first time, what does gravitational wave data collected by LIGO tell us, and what are some of the questions we are trying to answer using that data?
So LIGO is telling us about the incidence rate of black hole mergers and black hole neutron star mergers and neutron star mergers. And they're now, with the sensitivity of LIGO after its recent revamping, we're at a level where I think one of these events is being detected about once a week. So they're good statistics. So we're really learning about the mass spectrum of black holes in binary systems. And one of the surprises has been that the masses are quite large. The minimum mass of a black hole from a collapsed stellar object is about 3.5 times the mass of the sun. But most of the LIGO merger events involve black holes that are 10, 20, even 30 times the mass of the sun. So we've learned that, and that is still a bit of a puzzle, why so many of the LIGO black holes are well above the lower mass limit of black holes. We're learning about general relativity. We're learning that we've got affirmation of general relativity and how it works in the gravitational waves and how they're produced. We're learning about the population of black holes, of course, because the incidence of black hole mergers gives you a handle on how many black holes there are overall, because you're looking at the fraction where the black holes are in close proximity and eventually merge. So LIGO is really telling us a lot, but it's a slow process. We need years to gather data to draw statistical conclusions.
The next question is from Faisal, who asks, there are a number of countries racing to the south pole of the moon. Is there any cooperation, coordination, or laws to organize these missions to the moon?
No, there's very little cooperation, and there's certainly no law that applies to lunar exploration. China's had very good recent success sending robotic missions to this dark side, to the south pole of the moon. The south pole region of the moon, and Shackleton crater in particular, are of interest because there's appears to be large amounts of water, frozen water deposits in shadowed regions of these craters on the dark side. But there's no cooperation and there's no regulation of these missions. The moon has no governing body. The UN Moon Treaty of 1979 only says governments can't own the moon. It doesn't talk about private individuals or commercial operations, and it doesn't really put any constraints on lunar exploration.
All right, well, it is past 11 o'clock a little bit, so we're just going to end with one final question from Noob Hub Zero, who would like to know, are there more heavier elements at the center of the solar system due to hotter temperatures that cause stronger nuclear fusion?
Well, there are heavier elements in the center of the solar system because, of course, the sun is busy creating helium from hydrogen. As far as other heavy elements, though, the sun is composed of, it has a certain amount of heavier elements that were pre-existing in the solar nebula that formed the sun. So you have oxygen at about 0.1% of the fraction of hydrogen. So hydrogen is about 3/4 by mass, helium about 1/4 by mass, oxygen 0.1%, and carbon 0.05%. And so you have those kind of ratios of heavy elements in the sun itself, even though the sun is not creating any carbon or oxygen. Otherwise, all the heavy elements in the periphery of the solar system incorporated into the planets was again produced by previous generations of stars. And in that sense, the solar system is sort of a smelter because the heavy ash and the heavy element residue as the sun formed concentrated in these cool outer regions, and so the planets are really where the bulk of the heavy elements in the solar system are. Thanks for your questions. Been good variety as always, and thanks to Matthew for facilitating. And we have the next one on the books, and I think you said 2 weeks from now.
Yes, July 4th. So we will take a break from our holiday to come talk with you all. And many of you are not celebrating July 4th. That's an American holiday. But for those of you who are in the United States, you have the day off, hopefully, and maybe you can come join us for an hour while we talk about astronomy. So we will see you then. We hope that you have a great rest of your week. We hope this is a good way to start it off. And have a good couple of weeks till we see you again. Take care, everyone.